Greetings, the Astro 30 here, and I've got another kit to build today. This kit is what's known as a loudspeaker protector unit. What that does is it protects your loudspeakers from an amplifier if there is a DC fault condition. That is, if DC higher than a volt usually is present on the output, say one of the output stage transistors decided to short and allow the full line voltage on one side to go straight to the speakers. Let's just say your speakers won't last long. In fact, there have been reports that some speakers' voice coils have actually caught on fire because of the intense amount of current that would also be present with that voltage. So this is what this kit does, is it prevents DC going to your speaker. I mean, obviously there's a delay in time for reaction, so DC is still going to get to your speaker, but hopefully, even if it doesn't destroy the loudspeaker, it won't set the voice coil on fire if there's a fault condition. Now, this is the circuit board. This is a Clover Audio, Clover Pro-5.5. And the board is double-sided. It's nicely constructed. It's got some nice thick traces around the relays here. And they're using two relays, one for either channel, and they're strengthening the contacts of the relay by joining the two sides of the contacts together. So these relays, I believe, handle 10 amps, so that means theoretically speaking one relay can handle 20. So you'd need two relays, one for each channel, obviously. So that's the circuit board. Now this kit doesn't come with instructions, there's no schematic or anything, so what I did yesterday afternoon was I spent about an hour reverse engineering this circuit board back to a schematic diagram. So we're going to have a look at that now. Please excuse the crudity of this diagram, I didn't have time to draw it to scale or even to paint it. Now, the heart of the circuit is this IC here, which is a micro PC 1237. Now this is an NEC chip and it was made in around about 1986. Now, this being a new kit, I doubt that NEC make these ICs anymore. These are probably just cheap Chinese knockoffs like most of the stuff you find now anyway. So let's have a quick look at the data sheet to this IC. So this is the functional block diagram to the IC and each pin number here. We'll start with pin 1 and pin 2. Pin 1 is an overdrive detector. Now this would be used, an overload protector. This would be used for detecting like thermal overload, so you could connect a temperature sensitive device like a PTC or whatever to your heatsink, and if you have an over temperature condition, it can actually mute the speakers to remove that overload or that thermal overload. The second input, which is the important one, the one that this circuit actually uses, it ignores pin 1, is the output offset detector. Now that means any DC offset that's present on the amplifier. And most amplifiers have a DC offset of around about 100 millivolts. Any higher than that is considered a DC overload condition. That would just detect DC by rectifying it with a couple of diodes back to back, either positive or negative, until it reaches a certain voltage threshold that allows a transistor internally to turn on to let it know that, yeah, there's DC on the output, but it'll ignore AC, so it's only looking for straight DC. There's a flip-flop here, which we won't worry too much about that for the operation, because there's an extra pin here on pin 3 for either making this a latching state or a reset state, so we won't worry about that. Pin 4 is the AC off detector. That is when AC is applied to this pin from the secondary of the transformer. As soon as that secondary has gone, the relays instantly drop out. Pin 7 is VCC on mute. That is the amount of time it takes before the relays actually turn on for the first time as soon as power is applied. It's like a mute on function. So you've got instant off, delayed on. and it's just a simple RC circuit there to control the delay. And finally we've got a relay driver which then connects directly out to the relays to drive them. Now the absolute maximum ratings say that the power supply voltage is 60 volt, which is interesting because when you look at pin 8, which is VCC, it says the maximum pin 8 voltage is 8 volt. And the same for pin 7, which is the muting function, its maximum is also 8 volt. So you can't apply 60 volts straight to the chip, you have to put it through a voltage divider. But that's the things to keep in mind, are these maximum voltages. And pin 4, which is the AC off detector, its maximum voltage input is 10 volt. So these are things to consider when you use this chip. So that's all we're really interested in the data sheet, is the basic functionality of this chip. So as I say, pin 1's not used, it's grounded, that's the overload detector. This is the actual DC detector one, pin 2. And the way they've done it is, what NEC have suggested is to put it through basically a resistor divider here. It's basically acting as a mixer, so you have your amplifier in left here and in right there. It mixes the two channels together, so it's detecting from both power amps. Now because these are a high impedance, it's not going to matter too much to the power amp. This resistor network and this capacitor are basically forming a low pass filter. And if you're going down into the realms of 10 Hertz output signal, sometimes that can false trigger a DC protector circuit into thinking that there's DC on the line when it's actually a fairly low base signal. So that's all that's there for. Pin 8 is connected through a 2K resistor back to a 12 volt regulator. It's a 7812. Okay. So that's your VCC, and it's going through this 22K resistor into pin 7 through C3 here. This is the RC time constant I was talking about with the data sheet. That provides you with the turn on delay. They say in the description it's about 1 second, which should be enough. I tend to disagree. 1 second is not long enough for the filter caps and the amplifier to settle down after the first turn on transient. 3 seconds is about the average, but you can always change this value. They've provided a 50 volt cap for that, which is way overkill for what it's running on. So you could stick probably a 22 microfarad capacitor in there at 16 volt and it will still work just fine. Pin 6 is the output driver to the relay. Now this output signal is going to be negative based. That is, it's going to be switching the ground up through the relay because the relays are actually connected to the positive rail. I'll go through a basic equivalent schematic, if you like, of what this chip is doing inside, because there isn't one in the data sheet handy. But I'm just going to let you guys look at this schematic for a second and tell me what's wrong with it. Just pause and have a think of what's wrong with it. No, it's not anything to do with incorrect component values listed. I've just put all the component values that are in this particular kit that I received. So I'll give you a second to try and work out what it is that's wrong with this schematic. Alright, any ideas? Well, the voltage requirements of the relays. They're marked as 24 volt, and it's not a misprint. It does say on the body there 24 volt DC. Now we can see that the contact rating is 5 amp at 30 volt DC and 5 amp at 250 volt AC, which is fine. That's pretty average. But yeah, they're 24 volt relays. Well, 24 volt relays are not going to operate at 12 volt. There is just not enough voltage there for the magnetic field to be strong enough to pull the armature in. And I can test that on a supply, and we can actually see what the minimum voltage of this relay is for it to latch. But yeah, remember, we're only using a 7812 regulator here, so it's only going to be delivering 12 volts. And because this is switching negative, it's probably going through a driver transistor, obviously, so there's going to be probably 0.6 of a volt drop here, so it's not going to be the full 12 volts coming to the relay. It's probably more like going to be about 11.5 or something. So that is definitely not enough to pickle these relays. And even if you'd wired two of these coils in parallel with each other to reduce the impedance to 470 ohms, well, all you're effectively doing is you will require a little bit more voltage in order to create the magnetic field and draw more current. Remember Ohm's law, the lower the resistance or impedance is, the more current is going to be drawn across the circuit. So we can test whether or not these 24 volt relays are going to work in this circuit at 12 volts. And I can guarantee you they're not. Okay, so I've got the relay hooked up to the bench power supply, set at around about 12.1 volts, which is roughly what's going to be coming out of the relay driver. So we'll see what happens when we turn the load switch on. Well, we heard a click of a relay, but that's the relay internal to this. So if we look at those relay contacts, you can see they are moving ever so slightly, but it's not enough to pull the armature all the way to the electromagnet to make the contacts make contact. So let's find out what the minimum voltage that this relay requires in order to fully latch. There we go. Now I'm at about 13.8 volt, and as we can see, they are engaging and disengaging at 13.8, or more like 14 volt. So we know the minimum of these relays is 14 volt. But what happens when you have two of them connected in parallel, as they do in the circuit? Alright, so I've got the second relay connected up to the power supply in phase. The coils are in phase with each other. So let's turn the load on now, see what happens. Now, as you notice, the first relay is engaging, but the second one is hardly even moving. So this has got the same problem. And it could be the length of the wires here, but it's more of a voltage thing. So if I now increase the voltage, and now the second one has engaged. Now we're at 17.9 or 18 volt. So for two of these wired together, you need a minimum of 18 volts in order to make them engage. So that just proves that they're theoretically not going to work in the circuit. So I'm 100% certain that these relays are not going to work in this circuit. So what do we do about that? Well, we could change the regulator, because the maximum input voltage is 24 volt, and that would give you 33 volt DC roughly after rectification through the bridge rectifier. So you could change this to a 24 volt regulator. However, remember the absolute maximum ratings for pin 8 and pin 7 here on this IC is 8 volts. So you'd have to change this dropping resistor that they've got here, which is a 2K one, to something more like 4K7. Now, I don't know whether this is a parts error when they were putting the kits together, or whether this was intentionally designed with these relays in mind. These are OM-RON relays, and they do make a 12 volt DC version of these. So the other course of action is to change the relays, to which I have. I've got two 12 volt relays with the same pin out. They're both DT, that's dual pole, dual throw. They both handle 5 amps at the contacts at 250 volt AC. They both have the same footprint. If we compare it to the original one, they both have the same footprints, and the contacts are exactly the same. The two center leads here are the center common point of the relay. That's normally closed on that side and normally open. Center point of the relay contacts, normally closed, normally open. So these will work just fine in the circuit, and will actually work a lot better because the minimum voltage for these to operate at is around about 8 volt. And you have two of them wired in parallel at their coils. You're probably looking at more like 10 volt minimum for these to pull in. Without messing around with the resistor value here, because you need to know what the current flowing through this circuit is to calculate this resistor with Ohm's law correctly, or you could use a variable resistor without the IC connected to pin 7 and then just, you know, muck around with the resistance until you get around about 8 volts coming here at pin 8. Now, you shouldn't have to change that 22k resistor, that should be just fine, but you'd have to change this dropper resistor. However, what I'm going to do is I'm just going to use two different relays and forget about these 24 volt ones. Now, I had an argument last night with the seller about the ins and outs of how a 24 volt DC coil relay will not operate on 12 volts, and I am right, and I know I am right. And they offered me a 50% refund, so I ended up with $9.46 odd cents AU back. So thanks to that. And this, of course, is all before I've even built the thing. I haven't even constructed the circuit board up. It's still ready for parts. But yeah, we can just confirm first, before I go any further, that these relays will fit in this circuit board. See? They'll fit in there just fine. They're a little bit lower profile than the ones that come with it. There's a good 5mm difference in height there. No great big deal. So these relays will work just fine. Throw the board away. These relays will just work fine. Now, what I'm going to do though is I'm probably going to put some little fly leads coming off here, or at least one anyway, and then connect the other end to positive, and I'll connect it across the relay. I'll connect it across, well, one of these first to see whether or not it does actually work with these in the circuit, but I doubt it does, including having them joined together. I doubt it's going to work. Okay, so here's my take on what I think is going on in the circuit. Okay, we've got plus 12 volt rail at the top here. Just bring that back into shot. We have a relay coil with our flyback diode across the coil to prevent any back EMF going into the driver stage and blowing the transistor. We've got, this is pin 6 of the IC that we're going into now. What I reckon's happening here is we're going through a transistor, an NPN transistor like that, and that is connected off to the ground. So it's allowing a flow of electricity from ground up through to positive through the relay to turn it on. And most likely this is probably a Darlington driver, more than likely. Okay, and now for this to turn on we need that delay circuit in there, the RC delay. So I'll just extend this 12 volts here. So we're going to have, well, a resistor going through a capacitor to earth, and there's our R and our C, and once this capacitor is charged up to more than 0.61 of a volt, which is what the base input biasing voltage is of a transistor, is 0.6 of a volt or 600 millivolt, then this transistor or transistors are going to turn on, allowing the current to flow up through the relay coil, assuming this is a 12 volt coil. Forget the fact that the ones in the kits are 24. We'll get to that a little later. Now, how do we detect when the AC is disconnected? Well, that's just a simple matter of taking out that earth point, sticking in basically another NPN transistor which is connected to earth, and if we apply a resistor and a diode to the AC secondary like that, we're going to have smooth but rectified, half-wave rectified AC signal. So we're going to get mainly the positive potential coming in from the AC signal, which is what these NPN transistors need, is a positive on the base. So that theoretically will turn the base of that transistor on, which will then allow our current flow up through the driver stage, up through the 12 volt coil of the relay to turn it on. And as soon as this AC is disconnected, well, there's no connection to ground anymore, so the relay turns off. Now, with that, we need to have a protection circuit involved. So I've written off here. Now, when it detects either a DC voltage or an overload condition, it'll send an off signal to this circuit here. And basically you can imagine that as another NPN transistor with a positive feed on the base there, and that connected to earth. And all that's basically doing is allowing negative to flow up into the base of this transistor here, biasing it off or reverse biasing it. So if you reverse bias this transistor now, even if there is a forward bias here, the transistor will turn off, therefore the relay will turn off. And we'll forget about the flip-flop and all that other stuff inside the IC here. You've got pin 1 there, pin 2 there. This is pin 7 of the IC, and pin 8 is the VCC, but I haven't shown that. But you can just imagine it comes off of there, so that's pin 8, which is VCC. And that's basically all it is. That's overload, which is for heat or whatever you want to detect, even a voltage overload if you wanted to. And this is the DC offset. And so as soon as the DC voltage, either positive or negative, is applied at that pin with respect to earth, it's going to allow this transistor to turn on, which is going to allow it to conduct from the negative through to the off terminal, which is going to effectively bring this base to earth, shutting the circuit off. And that's basically how this speaker protector IC, and in fact any speaker protector circuit, works. It's very simple. There's different variations of how you can do the AC detection in design realms and stuff like that, but this is just a basic breakdown of how that IC works, and that's it. So what I'm going to do is I'm going to assemble this board. Now there's nothing much to it. There is supposed to be a heatsink for the regulator IC. They don't supply one. What else is new? So I'm either going to have to go out and buy one, which I forgot to do this morning when I was buying the relays, or just go without. So, but I don't think there's anything gotcha wise with this. The bridge rectifier is a small little IC type package, so it should be printed on the actual body of the IC which way round is what. Indeed it is. You can see there's a positive marking, a negative marking, and 2 AC markings. And on the PCB you see there's a positive marking, a negative marking, and 2 AC markings. So it's not that hard to actually get this the correct way around. Obviously that's not in the holes properly, but you get the point. Now the only thing with this is that I had to work out is what the heck was CD1 and CD2. CD1 and CD2 are these two 47 microfarad 50 volt orange coloured capacitors, and they are apparently 125 degrees Celsius. That's all it says. There's nothing really spectacular or fantastic about these caps. They're probably not even low ESR. Who knows without putting them on an ESR meter, right? And these are apparently a GXE brand. I've never even heard of that one before, probably some Chinese thing. So that's what CD1 and CD2 are these two capacitors. But yeah, as I said before, there is no schematics available online for this. There's no instructions anywhere. I've already Googled. So I reversed engineered it, and that's when I found the relay problem and thought, no, hang on, that's not going to work. So I've theorized that it's not going to work. I will build it, and then I'll test it with the original relays out of circuit, like it won't be actually soldered in, just to see if it does work, which I doubt it does, just to prove whether I'm right or wrong. And then I'll use the 12 volt relays. So what I'm going to do now is I'm going to put all the parts on the board that are bar the relays, and yeah, we'll go from there. And speaking of heat sinks, I've just found another one of these heat sinks on this switch mode power supply, which I can't even remember what it's out of now, but I'm glad I kept the board because I'm going to pinch that heat sink for the 7812. Okay, assembly's coming on. I've got the capacitors and the IC installed. With these input-output connectors for the speaker terminals, they actually just lock together like that. You push them together and they stay as one unit. You do that for both sides. And for some reason I ended up with an extra 10 microfarad 50 volt capacitor in the pack, which doesn't go anywhere. How nice. Anyway, I'm going to continue on with construction, and I've still got these connectors to mount, plus the IC on a heatsink, and then we're pretty much ready to go. Except I've noticed a problem, that the footprint of these connectors doesn't line up with the board. It's like a good millimeter out each side, so that's kind of disturbing. And good luck trying to get a screw into that screw hole too. So these are not actually going to fit that easily in the board, and well, yeah, now how am I going to fit a screw into either of these screw holes? That's going to be impossible. So I think for my own sake, I'm just going to leave those out because, well, they don't even fit there. Well, they do, but they hang off the board. But all it's ended up doing is just bending the pin. So the holes aren't even correctly measured and lined up. So I'm going to have to think of another idea for that. So I'm going to leave them blank and probably either have wires going in and out of it. You know, it's not really all that important. Next I'll move on to the regulator IC, and yeah, then we're ready for some testing. Okay, and that's the assembled board there. I've got the heatsink on. I soldered down the IC first before tightening the screw. This IC1 here, pin 1, it's not marked on the device, but you've got the top of the IC looks like that, then it goes flat. So where the chamfer is, that's the side you face to, and pin 1 is on the left. Anyhow, I have got some fly leads connected for the input of the speaker side. Got 2 fly wires for the relay and 2 fly wires for the AC. Now I don't have an AC transformer to test this on, so I'm going to test it on DC. However, if you look at the schematic for D1 here, this is the loss of AC detector on pin 4. This goes to one AC line, so this is an anode, therefore it's only going to pass a positive voltage through that way. So my positive from my power supply has to be on this anode. So I have actually marked on the connector a little black mark where I'm going to connect my negative. And yes, it's still going to go through the bridge rectifier here, but that's not really a great big deal. There's going to be about 1.4 volt drop there. But I'll just make sure by pumping in 18 volt DC to this that there's going to be plenty of headroom here for the voltage regulator to work. So first I'm going to plug it into the power supply, and I'm actually going to do some tests to see whether or not I have any voltage output at this relay. Also, this light, theoretically according to this schematic here, where we've got the LED here, that should come on when the relay comes on. So let's pop you on the floor, hook up a power supply and see what we get. Okay, so I got a little excited to see what happened when I first applied power before I shot this sequence of video, and indeed the blue light does light up. So 18 volts DC connected this way around as I've got it, seems to work fine. So if I turn the load on now, you will see that the blue light just came on and we have about 11.5 volts at the relay output. So we now know that a 12 volt relay should be pulled in by now. However, the penultimate question is, will one of these, or at least one of these 24 volt relays pull in? Well, let's turn the load off and find out. Okay, I've got the 24 volt relay connected. No. So no, there's not enough power for or enough voltage I should say, for the relay to even pull in. So I was 100% correct. So let's connect up a 12 volt relay and see what happens. Okay, got the 12 volt relay hooked up. We're still at 17.9 volts. The only thing is you can't see through this relay, but you should be able to hear it click. And I just heard it click. It clicked in. Theoretically, we should have a continuity across these two outer contacts. So I'm going to hook up the meter in continuity mode or resistance mode and see if we do. And indeed we do. We have about 1.1 ohm. So if I turn the load off, we have no continuity. And now we have continuity. Now, that's with only one relay connected across the IC. So what about now if we connect two of those 12 volt relays in parallel as they're going to be soldered into the circuit? Is that going to have any effect? Let's find out. Okay, I got both relays hooked up now. Now remember, these are 280 ohm coils. So effectively now we've got 140 ohm across that output IC. So let's see if both relays pull in. I did hear two individual clicks. So if I now carefully measure across these two outer contacts of this relay, I indeed have continuity at those contacts. I should have on the other side as well. Indeed I do. So if I kill the load, that should now be open circuit, which it is. So we have continuity now over in the normally closed position. So I now know that that circuit is working fine. So next test, before I solder the relays in finally, is we need to apply a DC voltage across these inputs and see if the actual speaker protector does what it says it's supposed to do. Alright, I'm down to one relay now, and I'm measuring the contact continuity via the meter, so I'll turn the unit on. We've got roughly a 2-second delay there before the relay clicks in. We've got continuity, so I'm going to use just a regular 9 volt battery, so it's separate from that power supply. And I'm just going to touch the 9 volt battery either way round to the inputs and see it killed. It stopped. It disconnected. Now the thing is, now that I've done that, it doesn't automatically reset. So I think it keeps it in protect mode. Oh, there it goes. It took a while, probably about, I don't know, 6 seconds. But it came back. So we know that that's working. So if I now try the battery the other way around, it drops out. And it came back again. So we know that when there's DC on this input, it is actually going to remove the output from the relays. So the speakers are going to be disconnected. However, there's a good 1 second lag there. So I'll do that again. Well, that was actually quicker that time. Yeah. Now that's interesting. Yeah, there was a good 10-second delay there when I had the positive of the battery connected to the input, so I've got a positive DC voltage going in. It took a good 10 seconds for the circuit to reset. If I switch it the other way around, so the positive's now on the ground and we're having a negative DC voltage going in, it's only about 2 or 3 seconds. Okay, but we know it's working. So I'm happy. I can now solder those relays in, and yeah, and that's the circuit finished. Okay, so there's the relays installed now. I can do one more final test on the power supply. That LED got bent for some reason. Do one more final test on the power supply. Okay, load on. Both relays clicked in. 9-volt battery test again. It's off. And it'll eventually come back on. There it goes. Other direction. And there we go. It is working as expected. I'm not exactly sure how hot that heatsink's getting. It's only like probably a maximum of 50 mA being drawn by these two relays, but when you put it on actually unfiltered mains on the secondary side, it's probably going to heat this IC up a little bit hotter because it has to deal with ripple rejection as well. But no, that's working. Seems to be working fine. So we know that this kit does work and it does what it says, just not with 24-volt relays. So I don't know whether this is actually an error in the parts when it was supplied in the kit. They stuck 24 in there instead of 12. But yeah, if you get one of these kits, there is a link in the description to where I found the eBay item. If you get one of these kits, double check these relays because you may have to replace them with what I've done here with 12-volt relays, because the 24-volt ones are not going to work. So I was 100% correct in my initial judgment when I first drew out the schematic and said, hang on, something's not right here. I actually did some hard evidence tests to prove that, well, one relay needs at least 13.8 volt to turn on and both need around about 16 to 18 volt to turn on. So yeah, they're not going to work at 12 volt, and what we had here is 11.5 across those relays. It's probably like about loaded down, probably 9 volt now. Anyway, I'm the Astro 30, and if you enjoyed this video, please remember to rate, comment and subscribe below, and you can always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro 30 saying, see ya, happy speaker protecting.